Okay, so let's continue with the workshop, and following this very exciting morning session showing us how far or where potentially the metabolome can give us for the advance in the exposome. We are now going to continue with to advance environmental health research and especially decisions and policy decisions. We are now going to go in more detail to try to understand what are the technologies and how the technology has really made the exposome possible. And also we need to have a sense of which are those potential challenges for interpreting and working with the metabolome. So our first speaker is Erin Baker from Pacific Northwest National Laboratory. So Erin is a bioanalytical chemist. And among her area of research, she's really interested in being able to provide quickly many measurements to many different chemicals, to do it in a way that is both in a short period of time, but without losing the valuable biological information. And I think that's quite the critical element, is to be able to really understand and interpret what those measurements mean, because otherwise this would be all useless. So thank you, Erin, for coming.
Thanks for the opportunity to speak. I'm really excited to be able to tell you guys what we're doing at Pacific Northwest National Lab. And to go off of Steve's point is we would love to collaborate with people. Sometimes we have amazing technology, but we don't have the samples. So we're very interested in collaboration. So I wanted to start off with the main challenges, and I'm calling it the xeno-metabolite measurements for exposome, just because you have the exogenous, and I mean, there's so many different names, so I'm just we'll call it that for now. And Steve hit it right off the head, is you have very low concentrations of these xeno-metabolites, and you have very high concentrations in your samples. So you need a really high sensitivity instrument that has really good dynamic range to be able to detect all these different compounds. Also, you want to be able to detect both the xeno-metabolites and the endogenous metabolites at the exact same time, so you can understand the biological changes. Because longitudinally, your xeno-metabolites might disappear, but your endogenous metabolites might still be changing from the exposure levels you got earlier on. Also, you want measurements that cover thousands and thousands of small molecules. And the main challenge we have is many small molecules have the exact same mass, but completely different chemical structures. So it makes mass spec measurements really, really difficult. So I just want to give an example just to show you guys, and I'm sure you guys all know what I mean, but if you just take testosterone, and it has an exact mass of 288.2089188, and you look at it in the NIST database, we get 18 different options with the exact same mass. And you have structures everywhere from completely different things. So if I don't have any other separation and I just try to match on mass, I've got 18 things and my false discovery is horrible already. So what happens if I don't have the best mass spec in the world that can measure out to 7 decimal points? And I have a range that I have to look from 288.2 to 288.22. Then we already have 27 different options for this one single testosterone compound. So things are starting to get really hairy. Our false discovery rate's horrible. And I might say I have testosterone levels when really I have this ugly, long linear guy that who knows what that is. So we're interested in using ion mobility to add to mass spectrometry measurements because ion mobility is really, really fast. So it's got the high throughput, and it adds an extra dimension of structural analysis to your mass spec measurements. It's also a way of maybe shortening your LC runs because you get extra sensitivity, and you can increase your confidence because you learn about the structure and the mass at the same time when you take a measurement. So for people that don't know that much about ion mobility, and I wasn't sure about the background of the audience, here's just a simple explanation of what the ion mobility concept is you have a drift cell and you fill it with a buffer gas. And usually it's at about 4 torr, and you can go up to atmosphere levels. But you have a weak electric field that pulls your molecule through, and then you also have the frictional force of the collisions with the buffer gas as the molecule goes through. So if we have an example here where we have basically a benzene ring with a meta, two OHs meta or two OHs para, the para is a little bit bigger structure. So when it goes through the buffer gas, the para comes out a little bit later, and we get a nice separation of the two different structure types, even though they have the exact same mass. And the nice thing with IMS is that you can combine it right after LC, right after GC. It's very fast. It's millisecond separation. So as long as your separation technique before the IMS is longer, then you can do sampling in here. So with this example, if we have the LC and we have that blue peak, if you sample that blue peak with IMS, you might get 10 peaks out of it with the IMS. Then if you sample the blue peak in the IMS with mass spec, you need a TOF mass spectrometer because you have to do microsecond sampling of it. You might get multiple peaks in your mass spec for your IMS. And this is what it can look like, where you have a simple looking LC chromatogram, but then you start getting millions and millions of different features when you just select each peak, representing different masses, different structures, and then different elution times. But what happens if we get rid of the LC dimension? Because this is our time-consuming dimension, and everybody comes up to us and they go, I want to run 1,000 samples, but I want to look for metabolites, so I want to do it in positive mode. I want to do it in negative mode. I want to do it with helic. I want to do it with a reverse phase, And you're going, oh crap, I'm already up to 10, 15,000 samples. So how do I shorten that in order to get something that'll actually work? So we started, first we just got rid of the LC. We said, let's just try IMS for things that are difficult to separate in helic. And so we just used ribose 5-phosphate and ribulose 5-phosphate, completely different structures, exact same mass. And we get separation, not the best separation, but you do separate these two isomers. So if you mix them together, each one is supposed to have a Gaussian distribution. You can Gaussian fit your peaks and figure out the quantitation for the two different sugars. We also looked at fructose 6-phosphate, glucose 6-phosphate, and glucose 1-phosphate, and again, we were able to separate these guys out. And if we mix them together, again, we see nice separation, and you can Gaussian fit and quantitate the amounts of each of the different sugars. We thought this was really interesting, so we started looking at some of the xeno-metabolites, and PAHs especially have a lot of different options that can be isomers. So here with our dihydroxynaphthalenes, we were able to tell where the position of the OH was by how they went through the drift cell and ion mobility. We also looked at some hydroxybenzo of pyrenes, and again, the OH position caused different structural differences, so we were able to separate those. IMS isn't the cure for everything, though. There's times where, like with xylose and arabinose in negative mode, we get the exact same drift time, because all you have is different positioning of your OH groups. But you can do tricks with IMS also. You can add a little sodium into your sample, and you can get nice adduct peaks that separate, because the OH groups on this guy, they fold around the sodium, where they don't fold around the sodium so much with the arabinose. So we've been working on creating an IMS database, and so far we have about 800 standards that we've been running in both positive and negative mode to get drift times for the different molecules so that we could add those into possibly Metlin someday or some kind of Agilent database. And we've looked at endogenous PAHs, pesticides, herbicides, fungicides, insecticides, all kinds of fun different things. And one of our big worries was that we were going to have a linear line when we looked at structure versus mass, and that our correlation would basically be 1. But what we saw actually is we see great differences in structure with the small molecules. So the orthogonality is pretty decent. And even here, if you look at a mass around of 100, we have 10 milliseconds different in the span of the different structures for the molecules, which made us really encouraged, because with peptides, we actually have more linear alignment than with metabolites because the structures are just so different. So then what we did is we wanted to look at a limited detection study to see how well the IMS was doing. So we spiked in, I think I have 2, 4, 6, 8, 10, 12 different kind of xenobiotics or xenometabolites. And what we saw is if you just put them in water, so no matrix, anything, we see 10 picomolar as the lowest detection limit. And that's really nice, but that's not realistic. So you spike them in human plasma, and it goes up to 10 nanomolar is the minimum level that we can see for these compounds. So you lose three magnitudes when you put it in a more complex matrix. So we knew we needed to do something else. We got rid of the LC, but we need some kind of front-end separation, but we still want it to be really, really fast. So we started doing some FAIMS measurements. And what FAIMS is you use high field and low field, and it does basically dipole alignment. So IMS, the molecule tumbles through. FAIMS, it dipole aligns, it goes straight through. So it's a little bit of a different structural separation. The cool thing is FAIMS is tiny. It fits on the tip of your finger, where IMS, this is a 1 meter drift cell. So that's the difference between the two different technologies. But you can easily put the FAIMS right on the front of the IMS system. So what we saw when we did the FAIMS-IMS is, this is our FAIMS dimension on the bottom, kind of like an LC dimension, is we see separation in the molecules. And if we look at the different spectra, here's our different M over Zs. We see completely different molecules at different ends of the FAIMS spectra. However, we have a problem that currently the best commercial instrument for doing fast FAIMS separations doesn't have the best sensitivity. It has you lose about 50% of the sensitivity of your measurements as soon as you put the FAIMS device on the front of your mass spectrometer. So that wasn't, we didn't like that at all. And when we started looking at urine, and we just directly inject the urine into the instrument, we only see about 400 features with IMS because the high salt content of the urine. And then with FAIMS, we only see 250 features. So not very many features, and by adding FAIMS, it did not help at all with the contaminants in the urine. Also, what we saw is with our standards in water, our lowest detection limit, it's supposed to be 100 picomolar, but it moved from 10 picomolar to 100 picomolar when we added the FAIMS on. So we're losing detection, we're losing feature numbers. FAIMS that's commercially available right now just didn't seem like a good option for what we wanted to do. So then we started looking at different kinds of fractionation, or how can we make the sample simpler to introduce into the mass spectrometer. And we found this option from Agilent, which is called the RapidFire. And what it does is it's actually kind of an SPE cartridge separation prior to analyzing your sample. And you can use any kind of SPE cartridge you want. You can use a C18, you can use Helix, you can use whatever type, and it changes the cartridges really fast. You can load 12 cartridges at the same time. And what you do is you inject your sample, and then your sample comes down. These are just two different things in your sample. You wash your cartridge, and so all your salts and all the cruddy stuff kind of washes away. Anything that doesn't bind to the cartridge washes away. And then what you do is you reverse the flow of the cartridge after everything's bound, send that to the mass spectrometer. And what we were seeing is we're seeing really, really nice analyses for both plasma and urine. This is just using a C18 cartridge, where we're over 2,000 features here, but then we can add different cartridges and get even more features. And what we see is within these samples, we're seeing isomers. So this guy, you can see, has the exact same mass, 2 different peaks with the ion mobility. We're seeing similar nominal masses that if you have a low resolution mass spectrometer, they might get convoluted. And then also more isomeric separations in the urine. And when we start to spike our xeno-metabolites into the plasma now we're getting down to 500 picomolar for our detection limits. And the one thing I didn't tell you is that each rapid fire analysis coupled with the IMS is only 15 seconds per sample. We see the sample elute in 3 seconds. And so it takes that long to clean up the needle, wash everything, and go. So it's pretty amazing for a fast screening method. You can do multiple cartridges in a minute. I wanted to prove that I wasn't lying about the detection limits. So these are 2 of the compounds we spiked in at 1 nanomolar. We have really nice peaks. It's not just ugly noise that we're trying to pull out at 1 nanomolar in human plasma. And I went really fast through that. But So what I wanted to show you is that IMS can separate metabolites and xeno-metabolite isomers, and it eliminates the need for LC. We don't get the sensitivity of an LC, but we can do our analyses in 15 seconds instead of in hours. So if you want to use it as a fast screening method, it works really well. The sample fractionation prior to IMS using a rapid fire or some kind of offline fractionation technique is essential, though, because you have too much ionization suppression if you try and inject your sample in without doing some kind of pre-prep. And then the offline fractionation provides a mean for high throughput studies. The way we have it right now, if we do 15-second measurements for the plasma, we can do 240 analyses per hour. So then our challenge is really the data analysis for the 240 samples per hour. And then we're also working on higher resolution ion mobility measurements in our lab to increase the isomer separation even further. And we think this is a really good opportunity for enabling rapid library generations if you need to do different targets or doing large cohorts of samples and getting higher identification because you add that IMS drift time dimension in there. You also know which cartridge your molecule is binding because some don't bind to certain cartridges. And the compatibility with, you can do a lipid-specific cartridge. So you can do lipids, you can do polar metabolites, you can do non-polar metabolites, all with these different cartridges, and you don't have to change the LC around every time you're doing your analyses. And so that's, I'm a member of Dick Smith's group, so we have a nice big cohort of us. But our metabolomics group is actually pretty small right now. There's only about 3 or 4 of us working on the project, but we have a lot of fun with the technology development, and we're really, really excited with the new results. We actually only got the rapid fire the middle of April, so everything you're seeing has come off in the last 2 weeks. So thanks so much. And
So Yvonne Rusin, Texas A&M University, I'm a member of the committee. Thank you. It was a beautiful talk. Can you add perhaps to cover broadly the topic, which was separation technologies? It was a good primer on ion mobility, but if you would put this into perspective with other separation technologies, number one. Number two, how can you characterize ion mobility in terms of reproducibility lab to lab? Is there more reproducibility? Is there less reproducibility? Because a lot of the challenges with building databases is it depends on your separation, depends on your detection. So can you speak perhaps to that effect
Definitely.
as well?
Yeah, ion mobility is awesome for reproducibility. So all you have to do with ion mobility is make sure you have the same buffer gas in your drift cell and the same pressure and the same temperature. So a lot of times people just run at room temperature, which is, you can have variation in temperature. It doesn't have, as long as it's within like 5 to 10 degrees, but you can correct for that also. So the instrument measures the temperature and can correct for that, and then you just have to keep your pressure pretty constant, or you could normalize your pressure later. But it's actually a lot easier than LC, which has more cartridge variability in the packing of the cartridges, where here it's just a gas.
And so can you then compare ion mobility to other types of chromatography beforehand, just so we keep the focus broadly on separation technologies?
Yeah, so the GC kind of, I think, is the standard for metabolic measurements, and lipids are more in the LC range is what I see. But GC is very reproducible. I think GC is one of the most reproducible, but GC also needs to be derivatized. So with IMS, if you can just take your sample and put it in without having to derivatize, then that reduces the amount of time you need for that also. The GC is great, though, and I don't think we should get rid of any technique, and I think this might just be a way of screening things really fast, and then in order to go into an NMR or GC-based technique after that. I knew you would get up right after that.
Yeah, GC stands for good chromatography.
Yeah.
Now, still, if you have if you want to have ion mobility, you need to have ions. And the problem in ionization is a competition for getting ionized.
Right.
So if you forego any type of chromatography before you do ion mobility, then you have a lot of competition.
Right.
And so what you may see is a result of the competition rather than the endogenous concentration in your sample,
Right.
depending on the complexity and yada, yada, yada. So how do you comment on that?
So I like it that you can put ion mobility after GC and after LC. So if you do GC, you can do a PCI source, and then follow that with ion mobility separation. So then you have the GC dimension, the ion mobility dimension, and the mass dimension. So you don't even have to get rid of your chromatography. You can just stick ion mobility in, but it gives you that extra dimension, because we've seen that with 3 dimensions to analyze a database, you get so much fewer false positive rate than if you only have your 2 dimensions where you have your retention time and your mass. In IMS, you can also do the fragmentation following it. And your parent peak, since you do the IMS separation first, the fragment peaks all fall below the parent peak, so you know exactly which fragment peaks go to which parent peak. So there's no confusion if you do like a swath type approach of which fragments correlate back.
Good. Yes, and I would like to also ask you about, can you explain how does it work for the targeted versus untargeted metabolomic analysis, and do we need like special libraries, or is it going to work differently for the interpretation of your metabolites?
Yeah, and so pretty much everything we do is untargeted because like Oliver says, you have to ionize it first. And so if you're going to ionize it, you might just look at everything, because there's no point in just taking the quad and only looking at 400 if everything's already there. And then plus, if you're only looking at something specific, you can do your informatics approach from a specific way, then go back and look for other features that are changing, and then go and try and identify them in a different way. So it works really well. But yeah, the key is ionizing, and then you can look at everything globally after that. It doesn't take any extra time.
So it's going to really work as a screening tool, but not as a definitive tool for quantifying the different...
It quantifies great too. Okay. So that's so like the linear concentration curves I was showing, we show pretty good.
So it could be enough in itself without an addition. Okay, that's what I wanted to clarify, because it was not clear to me. Okay, great.
I wanted to ask if you've tried this for breath. Other people have and don't find it as productive as SIFT-MS, but I wonder if you've tried it.
So I haven't, but I know the Alstone guys actually have a grant.
Could you just state your name? I'm sorry for the people on the web.
Sorry. Albert Donnet.
Yeah, we haven't tried it specifically for breath. I haven't done a lot of GC with my ion mobility. That's one of the next steps I would like to do, is put GC in front of it. But I know the FAIMS people are doing it, and they're actually seeing some really interesting results for breath analyses with the ion mobility separations.
Peter Dorstein from UCSD. When you do the rapid fire, there's a few seconds of chromatography, actually, as you're alluding. Do you take that into account as well?
Yeah, and we actually are. So we take into, because the peak elutes over 3 seconds. Each peak is about a half a second wide, and so you'll see like them really, really tight. And so we take that into account, and then we take the cartridge into account. So everything that we've done is logged for cartridge and chromatography time on that cartridge.